Good evening, everyone. My name is Adam Murphy, and I'm here on behalf of the Biomedical Diagnostics Institute to talk to you about a little light theft, plasmonics for disease detection. Disease detection is something we've been doing since time immemorial, but it's something we can always be better at. New statistics are saying that 1 in 2 people will be directly affected by cancer in their lifetime. With the worrying prevalence of these diseases and the unbelievable importance of early detection for survival rates, disease detection has never been more important. Currently, the method we use to detect diseases is the assay. So a load of antibodies are bound to a surface, like what's in your blood after a vaccine. We then flow in a blood sample. Diseases like cancer have certain chemicals that are only present if you have that disease, and these latch onto our antibodies. We then flow off another set of antibodies, our red Vs, and these are all tagged with a fluorescent molecule. The more glow, the more disease. But we can always improve this, but there are various problems to improving them. We could research the antibodies, but research on antibodies can be prayer-inducingly expensive. We could also mess around with the dye molecules, but they can be complex and have issues with toxicity. We can modify the surface, though, and we can fix that with plasmonics. Plasmonics is the study of how light interacts with gold and silver, but like in these rings here, but on the nanometre scale, so down at millionths of a millimetre in thickness. Usually electrons orbit atoms like planets flying around, but in metals it's a lot like drunk guys looking for the one girl at a party swarming on the surface. If light comes in just the right way, at the right angle, at the right colour, waving in the right direction, the metal can steal this and absorb this light, but usually it requires big prisms and large whirring machines. But if you pattern the surface, you can get around that. My research involves creating these kind of shapes, like silver corrugated sheet metal. Each wave here is 100 times smaller than the thickness of a human hair. They're not the only shapes I can make. I can also make my little egg boxes. I like my egg boxes. I think it's incredible that we can control the shape and size of things on this scale. The important thing here is if you bind a fluorescent molecule near these surfaces, when they've stolen light, each fluorescent molecule becomes 20 times brighter. So you don't need nearly as many to get the same signal. There are 2 applications for this. The first is in your GP's office. If you don't need as much blood, you can use like what diabetics use to detect for insulin. And so you don't need to go to a hospital for a blood test. You can just sit in your GP's office and not sit on your hands waiting for results. It can be done there and then. The other application is in cancer detection. If every pair of antibodies and disease markers is 20 times brighter, then you need 20 times fewer. This is a much earlier stage of the disease. And you all know yourselves, and you can see here the importance of early detection. It's the difference between a 90% survival rate to a greater than 90% mortality rate. These deaths are avoidable, and therefore they are unacceptable. Everyone will be affected by cancer at some stage in their lives, either directly or indirectly. If we have to beg, borrow, and steal every photon of light that we can, then we must. If it will save lives, then I don't think there's anything wrong with a little light theft. I'd like to thank you all for your attention, and I hope you enjoy the rest of the talks tonight.